Right. So we have one little last bit of chapter 6, which is talking about molecular compounds. We went through ionic compounds and all this stuff, and we talked about the naming of molecular compounds, but we didn't really talk about what they are or how they're put together. So that's what we're going to look at today. Now, when we talked about naming, we said that what did we say was the main characteristic of molecular compounds? How do you identify something as a molecular compound? What makes it, yeah?
No metals.
No metals, right. Well, specifically no ions, but that usually means no metals. So we kind of define it as like not an ionic compound. So let's be a little bit more deliberate now and talk about what this is characterized by. So molecular compounds are going to be characterized by something called covalent bonds. What that means is that they have shared electrons. Remember, in our ionic compounds, we didn't share electrons. This ion had this many electrons, this ion had this many electrons, and they would just sort of be attracted to each other because positive and negative attract. In a molecular compound, electrons are shared. So let me show you what that looks like. We're going to do something called making an electron dot formula. In an electron dot formula, all that means is you take the valence electrons for an atom and you draw them on the atom as little dots. So we're going to draw dots around the atom representing valence electrons. For instance, hydrogen. We make the symbol H, and how many valence electrons does hydrogen have? 1, so we'd make a dot. Doesn't really matter where you put that dot, somewhere around there. Let's try another one. Let's try Cl. Chlorine is Cl. How many valence electrons does chlorine have? 7. Yeah, it's in column 7A, so 7 valence electrons. So we'll put 7 electrons around. Now we could just sort of scatter those around and just put 7. But we want to use these for some things in a little bit. So it's going to be helpful if we pair those electrons up and draw it like this. 7 valence electrons. The reason we do that is really just for a visual clue, because we know that a lot of atoms want 8 valence electrons. We talked about that with making ions, that they gain electrons or they lose electrons until they get to 8. And so if we have them paired up like that, it makes a really easy visual cue as to how many more electrons it needs to get to 8. So if you see it written like that, you can see, okay, one of those dots is missing its pair, so that means chlorine is going to want 1 more electron. Now, when we talked about ionic compounds, we would say, okay, chlorine can gain an electron and then become a -1 ion. But there's another way that chlorine can get its 8 electrons that it wants, and that's by making a covalent bond. So we can say chlorine wants 8 electrons. And one way or another way that that can happen is for 2 chlorine atoms to join together. There's 1 Here's another one, and I'm just going to draw it kind of mirror image with the dots so that we can see how they connect. We could say that each of those chlorine atoms wants one more electron. But rather than form an ion, what they can do is share electrons. If they share those electrons, what they end up with is something like this. So in order to share those two, those chlorines have to be close enough together that the electrons can be in the valence orbitals of both atoms at the same time. We know that atoms have a particular size, so if they are close enough together, the outer electrons actually overlap, and they end up in both valences at the same time, and that's what we call a covalent bond. Those electrons are in both atoms' valences. So that means when we recalculate the valence electrons in the compound itself, in the actual compound, we can use those electrons for both atoms. So we can say that this chlorine has 8 electrons in its valence shell, and we can say that this chlorine has 8 electrons in its valence shell. So those middle shared electrons count for both now. And that's what we call a covalent bond, and that's why these molecules form. If the atoms are close enough to each other, the electrons can occupy both valences and count for both octets. So rather than having to transfer electrons, they can simply hang around each other and still have the same good thing happening, same stability. So that's called a covalent bond. Now, we might use these dots to figure out how that's going to work, but when we draw it, we usually don't use the dots. We usually use a line. So a lot of times you'll see molecular compounds written like this, with a line in between them. And that line is the same thing. That is a covalent bond that represents 2 shared electrons. And sometimes we'll even mix it and show all of these non-bonding electrons also, these other electrons. But it's really important that that line has this specific definition in chemistry. We don't use that line for things like ionic compounds because those aren't shared electrons. So we don't say NaCl and have a line between Na and Cl. It only applies to this type of interaction called a covalent bond, where the electrons are being shared. So by looking at the electron dot formulas, we can kind of figure out what the structure of a molecule might look like. And there's a whole bunch of rules and techniques for doing this. We're not going to go through all the ways of doing it in this class. We're just going to look at some simpler ones. But what you do is something like this. Let's say we want to figure out how carbon and hydrogen could connect. So we want to figure out a structure for this molecule CH4. That's 1 carbon and 4 hydrogens, same as methane. We want to know how those connect. So what we can do is look at the valence electrons and see if there's a way that we can make them connect so that all of the valence shells are satisfied. They're all full. So we might draw a carbon and draw a Lewis structure or a dot structure on that carbon. So how many valence electrons does carbon have? 4, right. So we can draw 4 dots around the carbon, like that. And how many valence electrons does hydrogen have? We already did that, but 1, yep. So we can make the hydrogen. And in fact, we're going to have 4 of those. So we can, I guess, draw out 4 of them. Now we know carbon wants 8 total electrons in its valence shell. How many electrons does hydrogen want in its valence shell? It can't get 8 because there's not enough there. How many electrons fit in that first bucket? Yeah, 2, right? 2. So since there's only 2 electrons that fit in that first bucket, hydrogen can only get a max of 2. Can't get to 8. It just doesn't have enough room. So hydrogen wants 2 electrons. Carbon wants 8 electrons. Is there a way that we can arrange this so that that happens? Do we have enough electrons here to make that happen? Nodding your head? So how? Listen. What? Yeah, we can share them around the carbon. So let's see if I can do this with the magic of technology. So if I put the carbon over here, I could take a hydrogen, kind of pair it up here, and now we have those electrons being shared between the two. I could do another one. It's going to get weird, but I don't know if I can rotate this thing. I don't think I can. Okay, so that's not going to work. I'll have to redraw it. But anyway, you can see how you can kind of rotate this around and match those all up. So let's do that.
Why does carbon want 8?
Yeah, why does carbon want 8? Where does that come from? Anybody? How do we know that number? The what? That's right. So the valence shell is full with 8 electrons because we know that there's 8 total that can fit in that second bucket, which is carbon's valence shell. So if it has 8 total, the bucket is full, and we know that's a good situation. So most atoms below, except for hydrogen at the top, want 8 electrons in their valence shell. That's called the octet rule. That fills up the bucket and makes them especially stable. Go ahead. You don't believe me?
No. So a carbon is up there numbers, it has 6 electrons, right?
4. Oh yeah, 6 electrons,
6
right?
electrons. So now I'm going to do the buckets.
Yep.
And I'm going to put 2, and then I'm going to put, well, out of 6, there's only going to be 4 left.
Right.
Okay. So how are you getting? Where did you get 8? And what bucket are you filling?
The second one.
The second, but there's only 6.
But there's only 6 electrons total. So that means a carbon atom just by itself is not going to be terribly stable. Not going to be happy. Because its bucket's only half filled.
Just grab 4 more to make it a 8 bucket, or?
That's one way you could do it. And then this is another way you can do it by sharing electrons with other atoms to get to 8.
So I'm always going to know whatever element it is, it has to have a full bucket.
Mm-hmm.
So even if it's not 8, I'm going to make it 8. But
Unless
I
it's
don't know
hydrogen.
where I'm pulling that to fill the bucket.
Right, because you
I'm
could
just filling it.
you could pull it from nowhere and make an ion and just like, you know, put some extra electrons in there. Or if there are other atoms that are meant to connect also, we can share them all together. And that's what we're showing here. So when I connect all those atoms together, those 4 hydrogens and the carbons, what you see is now there are 8 electrons around carbon. So that's another way of filling that bucket, is by sharing the electrons that come from other atoms. So each of those hydrogens brought 1 atom from its valence shell, or 1 electron from its valence shell, and the carbon brought 4. So altogether that makes 8. So when they're all shared like that, we can see that carbon has 8 and hydrogen each has 2.
So then what did we do with the extra 4 that the bucket was filled with 8?
That's still in there. So those were on that carbon to start with. And then the other 4 came from the 4 hydrogens, from each of the 4 hydrogens. 1 each.
But originally, I'm just trying to understand.
Yeah.
But originally the carbon had 8. And now we
originally the carbon had
4.
4 in its
but we
valence
made
shell.
it 8.
By bringing the electrons from the hydrogens.
Okay.
Yeah. That's where the extra 4 came from. The 4 So we moved them around, but there were 4 hydrogens that each had 1. That's the extra 4 that then make 8. So that's what we have here. Now that can be done in a lot of different ways. It doesn't have to be hydrogen. Like let's try do the same thing with chlorine. Let's say we have CCl4, 1 carbon and 4 chlorines. We do the same thing. We draw the dots for the valence electrons and look for ways that we could connect them to give everything full valence shells. So we draw the carbon with its 4 electrons. And we have 4 chlorines, each of which has 7. So we'll just say that times 4. Then how could we connect those so that the carbon and all 4 of the chlorines have 8 electrons each, or have access to 8 electrons each? Yeah, we could do it the same way, where we surround the carbon by the chlorines and pair up that unpaired extra electron. And that would look like this. So we take that carbon with its 4 electrons, and we can put a chlorine here with its 7, and a chlorine up here with its 7, and a chlorine over here with its 7, and a chlorine down here with its 7. And now, if we count that all up, carbon has 8, and each chlorine has 8 because of that sharing. Is that screen flickering? Is that just me? Is that annoying? I don't think I'm telling that. Is that better? That's all I can do. That's as far as my repair skills go. You hit it hard enough. Maybe it works. Still sort of flickering, but oh. Okay, so this is how we would build these things and decide how things go together. Now, normally we wouldn't leave them in that format. We would take those shared electrons and turn them into lines to indicate that those covalent bonds. So the one up here, we would draw like this. And the one down here, we would draw like this. So the dots help us put it together, and then we would use the lines to show how it's connected more clearly. So in those 2 examples, it's pretty clear what we need to do. We take the one thing in the middle, and we put the other extra ones around it, and then everything works out. It doesn't always work out so nicely like that. So let's look at another example. Let's look at oxygen, O2. How many valence electrons does oxygen have? 6, right? So we draw 2 oxygen atoms with their 6 dots. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Make sure we can see those dots. Okay. So this looks like we're going to start the same way. We've got some empty spaces. We connect the electrons. We fill it up. So we might say, okay, let's say we're going to take these two and share them. And that gives us this, where the two oxygens come together. Okay. So does oxygen have an octet now? Does each oxygen have 8 electrons? If you count the shared ones? Does not. You see that? Just 7. So that tells us that that's not actually really a good structure for oxygen. That oxygen doesn't just share a pair of electrons. But we know that compound exists. Does anybody have another idea of what we could do? Yeah, we could share more than one pair of electrons. I never said that only 2 electrons can be shared covalently. We can share more than 2 electrons covalently too. So we could take these other 2 unpaired ones and share those also, and we could kind of squeeze them in here so that all 4 of them are in there shared between 2. So now if we count all 4 of those electrons in both atoms, along with their original ones that they're keeping to themselves, does it work? Do they each have 8? They do. You see that? We can count 8 electrons in each of those circles. So the way we would draw that is by 2 lines instead of just 1. Each line represents 1 pair of electrons. So we can use 2 lines to represent the O2 compound. And we call that a double bond. So we're saying that those oxygens are now sharing 2 pairs each. Okay. So now I want you to try it and give you a couple to try. Same technique, draw the dots, see if you can get them to connect, and then draw them with lines at the end. So the first one we're going to look at is H2O, water. And then take a look at N2, nitrogen, which is nitrogen gas. Draw those dots. Think about how they might connect up. If these partition things are annoying, you can pull them out down the table.
Probably
But that's right. So you just well, they don't connect to each other. Oh, so you put like next to them, each side or something. Right. Yep. All right, looks like saw some good ideas over there. So let's take a look at what this would look like. So we're gonna do the same way. We're gonna draw those valence electrons, 1, 2, 3, 4, 5, 6 for oxygen. And then for hydrogen, we've got 1 each. And I drew them around that middle one so we can try to connect them up. We know oxygen wants 8 electrons total and hydrogen wants 2. So we can make those connections here and here so that they're shared. And then when we draw the structure out again, we leave everything else the same. We just kind of neaten everything up to show that those two are getting shared and these two are getting shared also. And then we check, are there 8 electrons around oxygen? Yes. Are there 2 electrons around each hydrogen? Yes, so that must work. If we want to then extend it to using lines, we just replace those shared dots with lines. Make it something like that. If you drew yours like straight across, that's fine. Same thing. We're not talking about the shapes because these aren't the real shapes of the molecules anyway. We're just trying to figure out how to connect them. So they could be straight across, they could be up and down, they could be side to side, whatever. As long as you've got the 2 hydrogens connected to the oxygen in the middle and not to each other. That works. Okay, the other one we looked at, N2, nitrogen. Nitrogen has 5 valence electrons, so we've only got 5 dots there. And since it's a pretty simple formula, just 2 nitrogen atoms, that means we're going to connect them together. So we know that much. Now we just have to figure out how we're going to connect them. So we can connect these two, but what do you find when you add those up? There's what? Yeah, there's still too many electrons by themselves. There's still not enough electrons on each nitrogen because we need 8. If we connect those 2, that gets us closer. That gets us to 6 each instead of 5 each, but it doesn't get us to 8. So what do? Yeah, we got to make 3 pairs. So we're going to connect those 2. We're going to connect these 2. And we're going to connect these other ones over here. 3 pairs of electrons that we've made between those nitrogens. So to redraw that, we put those 3 pairs right here. Because they're all shared. And now we have 6 electrons for each nitrogen. So we're going to draw that as a triple line. 1, 2, 3. And that's our dinitrogen compound.
I just ask a question.
Yeah.
With the nitrogen, you started with 6.
5.
5. Why couldn't you, how do you know that if I'm looking at that, why did I put 2 on the top and then 2 inside the end, and then with my other end I put 2 inside the end, and then I would match the 2.
Right.
How do you know where those dots are going on that element?
Yeah, good question. So one answer to that question is it doesn't matter. If there's 5 electrons, there's 5 electrons. It doesn't matter. It makes it easier to make the compounds and see the connections, though, if you try to space them out as evenly as you can on the 4 sides of the letter. So if we go, like you said, like 1, 2, 3, 4, 5, that's fine. There's nothing wrong with that. That's a perfectly good electron dot structure for that atom. But it makes it more clear where the connections need to be if I try to kind of distribute things around. So if I go 1, 2, 3, 4, 5, now I can see, oh yeah, I've got 3 unpaired electrons there that are going to need to be connected to something to make it to 8. Does that help? Okay. All right. We're going to try this more, but one thing that we learned from this, or that we can generalize from this, is there's a set of compounds or a set of elements in the periodic table that when they exist by themselves, they always exist as a molecule of 2. And those are called diatomic molecules. And it's important to know which ones are which, because when we go on and talk about chemical equations, we need to know their formulas. They're always like some formula and then with a 2. So some symbol and a 2. The ones that do this are the ones that we've just been talking about, the ones that can share electrons to get to 8, or 2 in the case of hydrogen. So it's hydrogen, nitrogen, oxygen, and then the whole column 7A. So fluorine, chlorine, bromine, iodine. None of those elements will ever just exist by itself. So when we're getting a container of hydrogen gas, we're never just talking about H, we're always talking about H2, the diatomic molecule. When we've got some oxygen, it's never just O, it's always O2. When we've got some chlorine, it's never Cl, it's Cl2. So that's why those are important. When we start writing chemical equations next week, we need to know that when a compound says, or when a problem says this thing was reacting with oxygen, we're dealing with O2 and not just O. That's going to change that. So kind of keep this in the back of your head for now. We need to know about diatomic molecules. We need to know which ones are which. Let's look at some bigger electron dot formulas and see what we can come up with. So let's look at CO2 and N2O. Go ahead and give these a try. And then finally SF2. So see if you can come up with structures for these 3 compounds, these 3 molecules. they kind of pair them up so that each atom gets 8 electrons. All right, let's take a look at these. Don't worry if you haven't finished them. Just want to look at it. So I looked around a lot of good structures, especially for the first one here. So we take our carbon with 4 electrons, each oxygen with 6. And that kind of works out because we see we compare these up like that, and then the other ones can get the other ones. So any unpaired electron wants to find its pair is another way of thinking about this and doing it. And that means one oxygen is going to be on one side sharing 2 pairs, and the other oxygen is on the other side sharing 2 pairs. So we rewrite this like this. So that oxygen's still going to have 2 pairs, and that one's still going to have 2 pairs. And then we can write that in lines. So that's our CO2 with each sharing 2. All right, let's look at the N2O. So there's a couple different ways to look at this one. You could draw it. Well, let's look at the atoms themselves first, and then try to figure this out. So there's our N. There's our N. And there's our O. Now what that formula doesn't tell us is how these things are connected. Is the O going to go in between the 2 ends, or is it going to go over to the right of the 2 ends, or the left, or something, like on one side of it? So there's no way of knowing that just by doing it this way. We'd have to do some other things that we're not going to do in this class to figure that out. And that means that if I'm asking you to draw a reasonable Lewis structure, that's what these things are called, Lewis or molecule structures or dot structures or something like that. If I ask you to draw one, then I'm not expecting you to know that unless one of them works and one of them doesn't. So let's take a look at that. Let's assume, because everything likes to be symmetrical, so let's assume at first that the O wants to be in between the 2 ends. Did anybody start out like that? That the O would be, all right, so let's take a look at that one. So if the O is in between the 2 ends, Okay, that means I want to put an N here and an N here to match up with the unpaired ones. Okay. So, does that work? How do we determine if it works or not? What do we mean by does it work or not?
We need to do N double bonded with one.
Okay, we need to share. Yeah, so that's one thing that's not working here is, okay, let me redraw this so that we can count it out. We've taken care of the oxygen. Oxygen's got 8. But we've got a problem with the nitrogens. The nitrogens only have 6 each. You see that? Count out 6 there, including the shared ones. And so normally the solution to that would be like what we did with the oxygen. We'd share more electrons. So we'd say, okay, well, I guess that means that these have to be shared also. But what's the problem with that? Yeah, then we screw up the oxygen. So if we try to do that, then let's see. So what did I do here? I took one of these out and moved it over here. So now I've got this, 1, 2, 3, 4, 5, 6, 7. I still haven't fixed the nitrogen issue because now nitrogen's got 7. And I screwed up the oxygen in the process because now oxygen has 9. You see that? The 9 of them all around there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that doesn't work either. And if you keep running into this thing where something seems weird, it's just not working and not working, what do you think the solution is going to be? What's the problem? Because really, the more we look at it, we can't even really, there's nothing else we can do. Because if we add more shared electrons, we screw up the oxygen. But if we take them away, then the nitrogens don't have enough. So what's the solution here? Yeah, so it means that we don't have things connected in the right order because it's just not working. So that means that none of this stuff can work. Let's try something else. And one of the things that about this type of solving this type of a problem, which I think annoys a lot of people, is there is trial and error involved here. You got to try to put these things together in some way, see if you can get it to work out, and if not, it didn't work out, try something else. So it means we have to be good at evaluating whether or not it worked out by looking at the electrons and seeing if it actually if everything has an octet or not. So let's try that other way. Let's try instead to put an N in the middle and an O on one side and an N on the other side. Let's see if we can get that to work. All right, so if we do that, we can share here and here. And that takes care of the oxygen and the nitrogen. And then we can share one of these. What? Yeah, we got another issue, right? Because that last nitrogen still doesn't quite work. Yep, so that would be another way to look at it. This is an example of a structure that just doesn't really work with this technique very well. So let me show you what has to happen for this to work. We made this assumption that these electrons are bringing in these valence electrons and connecting based on pairing up their existing held valence electrons. But in reality, in real molecules, it doesn't have to be that way. The electrons actually get pooled into a big mix when the when the molecule comes together and redistribute it as needed. So another way, so one way that we can make this this structure work is actually by moving some electrons around. So if we take one of these and just kind of give it to this one, then pair everything else up. Then it actually works. We had to split up these electrons and move them around again. Oops. We end up getting a double bond to each side, having those electrons over there and these over here, and now everything works out. Whoops, not O there, it's an N. So that actually works. And there's another way to do this with a triple bond too. But that's not something I would expect you to be able to do. I just wanted to show you how this model sometimes breaks down and doesn't work out the way we want it to. And if you see that your molecules are having problems and you can't get them to fit together, you can try some different stuff, but at some point we may need a different technique altogether. So we'll try to keep to the simpler molecules where this actually does work out. So in this third example, it does work out. Did anybody get it to work? Yet? So some people? Okay, so let's take a look at it. So that made it to work. That made it work out? Yeah. So SF2 is going to be similar to H2O in that you have an O or an S, something with 6 valence electrons, connecting on 2 sides to pair those electrons up. So there's our 6 electrons on the sulfur. And we can put in the fluorine like this. Pair these up, pair those up, and we've got them all connecting. All right, so you can practice that as you go through the homework. Okay, the last part of chapter 6, which I don't know if we'll completely finish today, but we'll do what we can here, has to do with how. Do you have a question?
Oh, yeah, real quick.
Yeah.
Isn't it true too that it's like you're the O2 or N2, they're always going to have a double bond no matter what they're with?
No.
Because in the example,
Go ahead.
wouldn't they have to?
So O2 will always have a double bond.
Yeah.
N2 will always have a triple bond. But the other diatomic ones will have single bonds. Like fluorine, bromine, yeah, hydrogen. Those all have single bonds. It is true that oxygen and nitrogen are always having that multiple bonds. Okay. We're going to skip over this section, by the way, if you're following along in the book. We're skipping over the section about shapes, 6.7. But we are going to look at polarity and attractive forces, the parts on either side of that. What? 6.6, page 189. So one thing that we can figure out now that we know how to build some structures is how those structures will interact with other molecules of the same type. So how do molecules attract each other? How strong is that attraction, and what does that mean physically? It has a lot of physical consequences for things like boiling points, solubility, which things go with other things, all of that. And so that's really important. That's a big part of chemical interactions. So we do that by looking at what we call the bond polarity. A polarity just means that something has positive and negative sides. So if something is polarized, it means that it has a clear one side or the other side, a clear positive, a clear negative. And that's what's happening with certain types of bonds where we see this. So let's look at what that means. If we take hydrogen molecule, HH, and we think about how the electrons are shared. So we talked about shared electrons. We talked about that line as meaning that electrons are being shared. But what we didn't say is, are those electrons shared evenly or unevenly? Are they shared evenly between the two atoms, or are they more on one atom or the other? And if you were to guess with that molecule, what would you think? Are they shared evenly or not? You want to throw it out there? Evenly? Why? Just your feeling? Yeah, just because. Well, you're right. Yeah, that's a good hunch. Yeah, they're shared evenly. And the reason is because there's really no difference between the two sides of that molecule. You got H on one side, you got H on the other side. Why would the electrons be on one more than the other? Right? So they're shared evenly. Those electrons are shared, evenly. Okay, let's compare that to a molecule where they're not. HF. So an HF molecule, those electrons are not shared evenly. In fact, they are more on the F than on the H. So if we were to kind of draw a picture of that, we might look like this. Where the electrons are pulled toward the F. So in that symmetric HH, they're shared evenly. In the HF, the electrons are pulled toward the F. And when the electrons are pulled toward one side, that sets up what we call a dipole, or a polar bond, because electrons are negatively charged. Everybody remember that? So what happens to the side where they got pulled away from? There's going to be fewer electrons, less electron over there. So what happens to its charge? Well, the electrons are negative. If they move over here, what happens to where they used to be? It's going to be positive, because it's like they left behind the positive part because they're not there anymore. So the electrons are pulled toward the F, which means there's going to be more negative over here and more positive over here. And that's what we mean by a polar bond. When the electrons are pulled to one side, there's more of a negative on one side and more of a positive on the other side.
Why do we know that's being pulled? If I
Good
just start with
question.
H with a line to F, how do I say, okay, something's being pulled? Why?
Right. There's no way to figure that out by just looking at that, the way that we put it up there right now. So we have to answer that question. So thank you for moving us into the next part, which is how we figure that out. So yeah, how do you know, if you just look at some bond, whether or not the electrons are going to be pulled? You have to look at a quantity that describes exactly that, called electronegativity. Electronegativity we define as the ability of an atom to attract the electrons in a covalent bond. So when it's sharing electrons with another atom, how well does it pull them? Does it attract them? And it's a quantity. So it's something we look up in a table. I'm going to pull the table out from the book here. It's on page 189. And it looks like this. It's a unitless quantity, so it's not like a measure of something. It's just kind of a relative amount. So we say that fluorine has an electronegativity of 4, oxygen of 3.5, nitrogen of 3. You don't have to memorize these numbers. What we can say, and what you can remember, is that there's a trend in the periodic table. So if you look at the colors here, blue means lower electronegativity, green is medium, and yellow is high. So in general, there's a trend going from left to right, going from bottom to top of electronegativity increasing. The other way to think about that is just to remember that fluorine is the most electronegative element. It's the one with the highest value on this. And so everything else trends up toward fluorine. So the closer you are to fluorine, especially toward the top, the higher the electronegativity is going to be. So we use the difference between the electronegativity numbers to figure out what is going to happen in that bond. All right, so we did that HF one. Let's give ourselves a couple numbers to look at, and then we'll try it out. So the electronegativity difference, if it's between 0 and 0.4, we call that nonpolar. So there's no pulling of the electrons in one direction or the other. If it's between 0.4 and 1.8, we call that polar. That's when we're saying there is this pull of the electrons that leads to a positive and a negative side. And if the difference is greater than 1.8, that actually becomes what we call ionic. So in that case, we're saying that the electrons are pulled so much that they separate and they end up on another atom. We have an ionic compound. Now those numbers are kind of just rough guidelines. They're not like strict differences. We have to do some testing if we really want to know if something is ionic or not. But it's a good, we're going to look at some of that this week, I think, in lab, or next week in lab. But it's a good kind of a rule of thumb. So if we see, let's say, an HF bond, like we just did, we would say, okay, what's the electronegativity difference between H and F? Well, that would be 4 minus 2.1, which is 1.9. So that puts us right in that borderline between polar and ionic, which tells us the electrons are pulled very strongly toward the fluorine in that bond. What about an OH bond? Is an OH bond polar? What do you think? Yeah, 3.5 minus 2.1, so polar, right? 1.4? Yeah. Okay, what about a CH bond? Yeah, so that's going to be 2.5 minus 2.1, 0.4. So we would call that, it's right borderline, but those compounds are generally nonpolar. So that means there isn't this separation. Now we're almost out of time, but the consequence of that separation is what's really big. That when we have this separation and the electrons are pulled to one side, so there's plus on one side and minus on the other, that means that molecules can interact with each other more strongly. They can be attracted to each other more strongly because positive and negative attract. If it's a purely neutral, nonpolar compound, the attractions between the compounds are going to be weaker. And we'll get into more of the details on that on Tuesday. But that's really why we do all of this. That's the consequence of all that. One more thing to look at before we're done here, just the way that we draw this. So let's say we're looking at a molecule. We're trying to figure out if it's polar or not. So let's look at one of the ones we looked at up here, like SF2. So we look at the SF2 compound. And we say, well, is this compound polar? There's a couple things that we need to do to figure that out. The first thing to do is to look at the individual bonds and figure out the difference in electronegativity. So one, there's only one kind of bond in this compound, SF. Is an SF bond polar? We go back up to the chart. So S is 2.5 and F is 4. So that's 4 minus 2.5, which is 1.5. So is an SF bond polar? Yes. So then what we want to do is we want to go back to the molecule, our model of the molecule, and we want to draw how that polarity works. So we want to say the negative is on this side and the positive is on this side. So it is polar. Where is the negative in a SF bond? Where are the electrons going to? The S or the F? The F, because that has that higher electronegativity. So if the electrons are going toward the F, that means the negative part is on the F and the positive part is on the S. And the way we draw that is rather than just saying minus or plus, because that means ions, we use the Greek letter delta, and we say delta minus on the fluorine and delta plus on the S. Delta is usually used to mean difference. So we say it's not a full charge, it's not an ion, so it's not appropriate to just write minus or plus. That tells us that there's a partial separation of charge, that some of the electrons are moving more toward the fluorine. It's partially negative, and we would do that on the other one as well.
That you're writing next to it.
It's a Greek letter delta.
That's a D?
Yeah, but it's in the Greek alphabet. They have different letters. So that one's spelled delta. Lowercase delta to be precise. Because uppercase is like a triangle. So now we can see on that molecule where the electrons are going. They're going toward the negatives. They're going away from the positives. And so on Tuesday, we're going to use that to figure out the overall polarity of the total molecule and then how those molecules interact with each other in something called intermolecular forces. And then we'll get to try that out a little bit in lab. Is that good? Maybe? All right. Well, have a good weekend. Happy studying. And I'll see you on Tuesday.